get back to it. Before Rachel tells you about GRUs, I've just got a couple of follow-ups from previous lessons. The first is I lied to you. I told you our Turkish classification model was 89% accurate. Actually, it's 91% accurate. It turns out there was a bug in the FastAI library with parallel processing that was making it slightly wrong. So if you rerun it with the latest FastAI, you'll actually get 91, which is even better. And of course, we didn't do the backward model for that, so you could then ensemble that with a backward model to get better still. One of the things that came out of the translation was that the translated sentences, even in the version with attention, were not great in that they had like kind of repetition, a lot of repetition, and part of the reason for that is obviously we weren't using very much data, and we weren't using very much compute, and we were using quite a small model. Like, translation's difficult. The Google translation model has 8 layers of LSTMs. I think it's 8. And they train on a huge corpus, and they use a large portion of a data center to, you know, do that for a long period of time. We intentionally picked a small subset of a fairly small corpus. But part of the reason for the problem is the way that we did generation. So the get predictions loop, if we go back and have a look at it, I moved on from Turkish to the follow-up from the attention translation. The thing that, so Rachel had this get predictions method, and it just goes through one batch at a time, and for each batch it goes through one sentence at a time, and the key thing it does is this is with the result of the model, and the thing that came out of the model, the last thing is the actual predictions, and then we did an argmax to say which word has the highest probability, right? So this is the kind of the inference time decoder that we used, and this is what we would call a greedy search. And a greedy search is actually not a good way to generate text. So we're not, in the bit of the lesson I'm doing, we're not going to retrain a model at all. We're just going to say, if you have a trained model, how do you generate the best text you can? And so this approach that we showed you here of using a greedy word-by-word approach is the worst possible thing you can do. And so to give you a sense of why, think about this. Here are let's imagine that you've got a translation model, and it feeds you back the top 3 choices are all pretty similar probabilities, and it could be the or at or some. And then the second word, it gives you back 3 possibilities, and they are, you know, high probability, all about equal, could be fluffy or big or hot. And then the third possibility, all about equal, could be dog or cat or pig, right? So in the greedy approach, you would just pick the highest probability for each, right? So let's say the probabilities for each were like 0.4, 0.2, 0.2, they're all pretty similar, you know. And maybe this was like 0.4, 0.2, 0.2, and this was like 0.4, 0.2, 0.2, right? So the greedy version would say, oh, the answer, which our inference would be some, because that's the highest, fluffy, because that's the highest, pig, right, and then rest of sentence. But that doesn't make a hell of a lot of sense, because you don't normally describe pigs as fluffy, right? So what you would prefer to do is to kind of like figure out a path through this. This is kind of like a graph, right? We can pick at each point some node, and then we can create an edge to the next part, right? So there's like a huge number of possible ways we could go through this graph, right? If there's a long sentence. So there's, 3 possibilities here, and 3 possibilities here, and 3 possibilities here, and so forth, the rest of the sentence. And of course, in real life, we have thousands of possibilities for each possible word. So to solve, our way to solve this problem is to use something called beam search. And beam search is how we normally do, most people do generation for something like translation. Now what we do in beam search is we say, okay, we're going to go through each stage, but we're not going to just pick one possibility. We're going to pick k possibilities. We're going to pick some number. And that number k is called the beam width. So if we picked like k of 2, right? Actually, let's make these not all equal. So we can pick a k of 2. Then we would say, okay, after word at time point 1, it could be the, or it could be some. So they are 2 highest possibilities. And then at the second point, so then for each of the and some, we would rerun our decoder and get a new probability of each of these things given that we start with the, and each of these things given we start with some. Because remember that the RNN at each time step has as input both the hidden state, but also like what was the previous word you predicted. So at this point you can't just say it's 0.4, 0.3, 0.2, but it actually depends on your previous word. So based on those 2 words, maybe the 2 highest possibilities now at this point are some, fluffy, and the big. Okay. And so what we do is we pick only the top k. So k is 2 for us, beam width, 2 word strings, right? Because we could, for each of the and some, there are 3 possibilities, so there'd be 6 possible next steps. We just keep the top 2. So we just say, okay, at this point, it's either the, big, or some, fluffy. And then again, we do the same thing for step 3, right? So for each of these 2 possibilities, there's 3 words we can add on. And so for each of these possibilities, the decoder has different probabilities for each of those based on each of those possible inputs. And so we end up, and then we just select out of those 2 times 3 is 6, again, the top 2 3-word strings by probability. So in this case, the top might be the big dog versus, some fluffy cat. And so forth, right? So this works out nicely because if the next kind of 3 words turned out to be with high probability bit the postman, right? Then this approach allows us to identify that, like, oh, it's probably the big dog bit the postman. So it's only like partially greedy now. Okay, so it's a greedy approach, but we're keeping a beam width number of options all the way through. Coding this is a bit of a pain in the ass, so I'm not going to bother, besides which FastAI already has it. But if you're interested, you can go to FastAI and search for beam, say, and find beam search, and then you can click source code, And there it is. So it's kind of, let's see, 1.5 screens. So it's not lots, but it's just basically that doing that loop and selecting the top k at each side, time step, and here's that beam width that beam size you can pass in. Okay, so that's the kind of normal approach for decoding a translation model, and it's a good approach for kind of decoding any kind of text where you have a something kind of pointing you as to which way to go. So with translation, at every step, there's like something saying like, this word is probably that or that, this word is probably that or that, which is very different to the GPT-2 unicorn example we saw. Remember the GPT unicorn example was like, here's a paragraph of English text, now what might the rest of it be? And like that's got no guidance, it's not translating something, and that kind of text generation is very different. There was a paper, let's find it. So I'm now looking at the 7B sec-to-sec nucleus. Notebook, which has a link to this paper called The Curious Case of Neural Text Generation, which is less than 2 months old, so this is quite a recent paper. And this came from the Allen AI Institute, also known as AI2. And they pointed out something really fascinating, and this is like a pretty easy read, so for people who are just starting to get into reading academic papers, this is a good one to check out. They did something interesting, which is they said, what happens if we take the GPT-2 model and we do the unicorns prompt, exactly the same as in their blog post, and we use beam search? And the answer is they get the continuation, professor of the Department of Los Angeles, the most important place in the world, to be recognition of the world, to be of the world, to be of the world, to be of the world. Not great. And so it's interesting, they actually point out that beam search seems to have problems. So for GPT-2, what they did was they did what's called top K sampling. And so top K sampling is this. I will show you. So if you look at 7B sec-to-sec nucleus, what I've done... oh, by the way, if you ever see things like this, torch.cuda.setDevice in our notebooks or anywhere, that just means that I was running something on a machine with more than one GPU, and I wanted to pick which GPU I wanted. If you only have one GPU, that will give an error, so you should just delete it. So what I did was I didn't want to have all that cells and cells of code to rerun every time and copy it from other notebooks, so I just pasted it into a sec-to-sec.py module, just like we talked about the other day. Just makes life easier. So all the stuff from Rachel and Sylvain's notebook you can see there. So the one thing I did copy from the notebook was the sec-to-sec RNN with attention. So that's exactly the same. Like I say, we're not training a model any differently. And what I did was I trained a model for only 5 epochs to make it like particularly crappy, because I wanted to show you the differences when you're kind of working with a crappy model. And so I took the get predictions method, function that we just looked at, with that, argmax thing. But I also added in the actual raw activations, the raw probabilities. So rather than giving us back 3 things, the reconstructed X, Y, Z, it also gives us the pure probabilities. And so that lets us now write our own decoders, our own inference decoders. So then I wrote a top K decoder. So it's only 3 lines of code. And so we just grab the output activations, we throw them through a softmax to turn them into probabilities, and then we simply call the PyTorch top K method, which will just give me the top K highest probabilities, giving me both the probabilities and their indexes. And then so top K sampling just randomly picks one of those top K with like literally just a random integer. So that's all top K sampling is. So if you want to use top K sampling, you need to then put it into a decoder. So what I did then was I literally just copied and pasted the decode method and put it into a new function. And then I replaced the line which says in the decoder, I replaced the line that says dot max, and I replaced it with a line that says select top K. Okay, so that would give us top K sampling, which is would be the same as GPT-2, and so which is not bad. So this paper asked the question though, like, well, we thought beam search was meant to be the best way to do inference. Why is beam search so terrible? Why is it creating so much repetition, as we saw in the examples Rachel showed last week? And what they found was interesting. They looked at a few examples of sentences, such as this one, which is actual human-generated text, right? "Are you cold?" he asked, his voice full of concern. I just shrugged and squeezed my eyes shut. I saw Koja's glowing eyes and soared. And what they did is for each time step, for each word, they said, in a language model, what's the probability of the word the human picked? And what they found is sometimes, as you expect, the probability is right up close to 1. The blue is the human text. But very often, the human is picking extremely unlikely words. For example, Kojas. I've never even heard that name before. Whereas beam search, by definition, this is the probability of beam search picks a very, very likely thing at every point. So here's the beam search generation. He looks at the clouds, he looks at the clouds, he looks at the clouds, he looks at the clouds. Okay, so actually beam search, it turns out, generates very likely per time step speech, but very unlikely distributions. So this paper makes a suggestion as to how we avoid that, and it's basically to use, so they have a number of sections which describe like why does beam search have this problem, but what they then do, which is the main bit I'm interested in, is how do we fix it. And they propose something they call nucleus sampling. And nucleus sampling is basically top K sampling, but they point out something problematic about top K sampling, which is if you're doing top K sampling with K of 5, say, and your language model or translation model says, I am 99% sure the next token in this sentence is a full stop, then you shouldn't do top K sampling at that point, right? You shouldn't pick options 2, 3, 4, or 5, because option 1 is almost certain. Right? So top K sampling has its own problems. So they suggest something which is basically a top K sampling with a dynamic K. So changing the value of K each time. And specifically what they do is they say, let's do top K sampling, but we will pick K such that the total probability of those K words is something. And in that case, they pick 0.9. So they call it top P sampling. So they say, let's pick a K so that the words we choose from have a probability of 0.9. So in the case that there was one word that already has a 0.99 probability, then K is 1. So we just pick that one every time. In the case where our model has no idea what the next word is, and it's got like 20 things that all have like a 0.02 probability, and they're the top, then it might be a top, K of 20. So here is So now we've taken select top K and we turned it into select nucleus. That's what they call this algorithm. And so it's interesting, as is often the case, when you implement a paper in code, the thing you implement is often just 3 or 4 lines of code. So in this case we have 7 lines of code. And the step 1 again is do a softmax. And then step 2 is get the indexes which sort the probabilities, because we want to kind of do a cumulative sum to find how many Ks we need. And then just go through each one, calculating the cumulative sum of the probabilities. And when your cumulative sum is above P, then pick a random choice of the ones you've seen so far. And that's it. That is nucleus sampling. And so if we pick the greedy sampling that we used in the previous neural translation lesson with our, particularly crappy 5-epoch model, and we try to translate something which is meant to be what gaps remain in our knowledge of unknown on which future research should focus, the translation is for greedy, so kind of top K where K is 1, what gaps are needed in our work, and what is the research of the work, and what research will be in place to future. You can see like the crappy translation model has this, this repetition problem. If instead we switch out the greedy and put in nucleus, and then call predict with decode, which as you can see just puts it into eval, no grad, calls that decode, and then returns the reconstructed output, we get what gaps are needed in our understanding of work and security and how research will need to be put in place. So like it's a much less repetition, better sounding sentence. So I kind of just wanted to mention this. I'm not sure, like partly because after last class I asked the students if anyone is interested in pair programming a paper, and so we spent the afternoon, a couple of hours I guess it was, implementing this. So I wanted to kind of show you what that looks like, give you an example of a paper that's worth looking at, but also just have a kind of discussion about generation in the translation notebook. So far we've only talked about how do you train the model. We didn't talk about actually how do you generate text. And so these techniques of beam search and top K and nucleus top P sampling are the 3 that you probably need to know about. So that is that.
Sorry, you may have already said this. Is there a way to, I guess, generate text, or if you're generating text without those and just taking the top probability, do you end up with the repetition?
Yes. We saw that last week, remember?
Week, yeah.
Yeah.
I mean, some of that, I guess, how much does that relate to, I know, the temperature of, like, kind of how much randomness you inject at each step? How much can that help with it?
Yeah, so I guess that's another way you can do it is doing multinomial sampling, where you select from the full set with a probability based on the p-values of the softmax. I think, again, you kind of end up with the problem that the Nucleus paper pointed out around, like, you're going to end up picking overly high probability things too often. But, I guess, as you can see, this is only a 2-month-old paper, so I would describe this as a open area of research, and these are some current best practices. Now, I would say for translation, probably beam search is generally still going to be best, because it's this, like, it's not at all like open-ended generation. And it's only, in this case, the only reason we kind of needed it to look any good was because we have such a crappy translation model, because we trained it so quickly on so little data. I'm not sure anybody's tried Nucleus Sampling on high quality translation models. It would be interesting to find out. But the other place beam search is used all the time is like speech recognition. It's a similar thing, right? Speech recognition is basically translating audio into words. You use the same kinds of approaches, the same kind of languagey model, but you're trying to find something that the words match the audio, but also makes sense as a kind of complete end-to-end sentence.
Oh, thank you.